Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue further in our series on quantum chemistry. Since the previous session we are talking on free particles. So friends, in the first session we would be talking on free particles only, and we will be covering most of the portion on free particles so that you get in-depth knowledge, and we will be starting from the point where we left in the previous session. Friends, in the next session we are going to talk on rigid rotators. This is the very new topic, or the beginning of a new chapter 2, we can say that. For the discussion on the two topics, we have with us in our studios Dr. Amita Dua. Dr. Amita Dua is the Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dear friends, Dr. Amita Dua is the most appropriate person to talk on quantum chemistry because she has authored a book on quantum chemistry. So she has lots and lots of information for you on the respective topics. Let's welcome our guest, Dr. Amita Dua, once again, and let's try to understand the topics in detail. Hello ma'am, welcome to the lecture.
Hello and good afternoon to all my viewers. Today in the first session I will discuss about the free particle. We have already discussed few topics in the last few lectures, like I have discussed about the introduction of what is the difference between the classical mechanics and quantum mechanics, and after the discussion of quantum mechanics I have discussed about what are the postulates of quantum mechanics, what is actually the wave function, the types of wave function, the eigenvalue equation, and then I have also discussed about the operators as well as the postulates of quantum mechanics. Once we have discussed about the postulates of quantum mechanics, that how the quantum mechanics gets applied to the system, we have first of all we have discussed the first system, that was the particle in a box, and particle in a box is basically the translational motion which was discussed. And in particle in a box we have first discussed about particle when the particle is moving in one dimensional box, and then particle in 2D box, and in fact in the last lecture only we have finished with the particle in 3D box. So once it is finished, so we are just left with, in that particle in a box, we are left with free particle. That is, otherwise the particle was constrained in a box, like in 1D box or in 2D box or in 3D box. But today we will discuss about when there is no restriction, when there are no boundary conditions, it is not bounded in any of the region. Earlier there were the limits, that is the length of the box was 0 to A in 1D box, or 0 to B, and then in 3D box it was A, B as well as C. But now today we will discuss about the free particle, that is there is no restriction on the particle and it is free to move. So in the free particle, that is the unbounded, the free particle means that is the unbounded state is the one which is not subjected to any external force or potential barrier, and it is free to move in a limitless place. This means that particle is not in a region where potential energy varies with position, that it can move, that is, there is no height, because potential energy depends upon the height. Because there is no height, there is no limits. Thus the potential energy is, in this case, in the free particle case, we take potential energy to be constant, and thus we take V equals to 0. For our convenience, that is in the derivation part, we will take V equals to 0. Now we have to discuss about, because every time in the quantum mechanics, first of all we have to write the Schrodinger equation, and from the Schrodinger equation we try to get the wave function as well as the energy. And once the wave function is obtained because the wave function, now everybody comes to know that wave function is a storehouse of information. Once the wave function is obtained for any of the function, you can get any value like the potential energy, that is the total energy, like the momentum, the angular momentum, the velocity, the position of that thing. So once the wave function is obtained, you can calculate each and everything. So from the Schrodinger equation we try to get the wave function as well as the energy for the free particle, and now I am doing the derivation part. For a free particle, the Hamiltonian, because always my Schrodinger equation is H psi E psi, I have to write, first of all the first thing is always to write the Hamiltonian part, that is H operator. For the free particle, the Hamiltonian is given by H operator equals to minus H cross square upon 2m del square plus V, and this is already discussed few lectures back when I was doing operators with you. So at that time I have discussed the expressions of the operator, and I have simply taken the expression for the operator, that is H operator, that is Hamiltonian operator is minus H cross square upon 2m into del square upon V. My Schrodinger equation for the free particle is H psi E psi. So just by putting the expression for H operator, this will become minus H cross square upon 2m del square plus V bracket close psi equals to E psi. Because my potential energy is 0, so this will become my V factor, that is plus V in the expression for Hamiltonian, the V factor will become 0. So this is minus H cross square upon 2m del square into psi equals to E psi, because for the free particle we assume that potential energy equals to 0. So this is minus H cross square upon 2m del square psi equals to E psi, and now I am taking the negative part, that is minus H cross square upon 2m part on the other side. So the expression is minus H cross square upon 2m into del square psi plus E psi equals to 0. Now I will divide this whole equation by H cross square upon 2m, because I have to make a differential equation which is as simple as that, so that I can easily solve it. So this will become, by this I get rid of that H cross square upon 2m. So my equation will become del square into psi, because I have divided the whole thing. So it will become 2me upon H cross square into, otherwise it was E psi. Now by dividing, this will become 2me upon H cross square into psi equals to 0. So these expressions are very simple. Just go through the slides carefully, you will get to understand. Now what is my del square? My del square is simply the Laplacian operator, and the expression for the Laplacian operator is del square psi, because psi is also, my del square is simply del square by del x square, del square by del y square, or d square by dz square. So I have just simply put it into delta square, and because psi was already present, so this will become delta d square psi upon dx square, y square, z square plus 2me upon h cross square psi equals to 0. So simply I have put it the expression for the Laplacian operator. Now because my particle is in the free state, because there are no boundary conditions, otherwise in the 1D box or 2D box or 3D box I have got the boundary conditions. So whenever the boundary conditions are there, it becomes very easy to get the expression for psi. Although it is not difficult over here, but it was a method that whenever boundary conditions are there, then we apply the boundary conditions and get the values of the constants which are present. Because here there are no boundary conditions, so we simply apply the method of separation of variables to solve this equation. That is, for x, for y and z, we are making the 3 equations, and here the method is a bit different. Since the particle is in the free state, that is, it is free to move everywhere in the space, so there are no boundary conditions can be applied to such systems, and thus the solution, it lies in the method of separation of variables. Now how will you separate this? Now we will consider, I will split the wave function into 3 parts, that is x and y and z. This separation of variables I have also applied in when we were doing the solution of 2D box and 3D box, because again there were x and y, and in 3D there was x, y and z, and similarly in this case, because it is moving freely, so there are 3 coordinates, that is x, y and z. So my wave function, that is psi, which depends upon x, y, z coordinates, now I am splitting this wave function into 3 wave functions, that is capital X, which depends upon the coordinate x, the capital Y, which depends upon the coordinate small y, and capital Z. Again, these are the wave functions. Otherwise we always write the wave function as psi, because you are always there is in our mind that the wave function is psi, but you can give the expression, you can give any expression. So this will become the capital X, capital Y as well as capital Z, where x, y, z are also the wave functions of their respective coordinates. Now substituting this in the Schrodinger equation for the free particle. Now what was my Schrodinger equation? My Schrodinger equation was given in the expression, that is del square psi del x square, del square psi del y square, del square psi del z square plus 2me upon h cross square psi equals to 0. Now simply instead of psi, I will put x, y and z. So now this will become, first of all I am just putting it, and then the things which are constant, we will take them out. And so this will become del square psi del x square. Instead of psi, I am putting x into y into z. Similarly, del square psi del y square x into y into z, and in the third term also, and as it is I have just put it. Now because in in this expression the first term contains del square delta square upon del x square, so it depends only upon the coordinate x. So obviously it will vary with x only. My y and z terms will become constant, and that is why I am taking y and z as constant and d square by dx square into x only. Similarly, in the second term in this expression, the second term contains only y, that is why I am taking x and z constant. This will become del square by del y square into y as a function, and then x and y constant, d square by dz square into z as a wave function, and with 2me upon h cross square I have the total wave function as it is, which is present. Now I divide, because there are so many constants and I have to get rid of them, because otherwise the equation will become very difficult to solve it. So one by one I have to remove all the constants. So the first step for removing is that I will divide the equation again with x, and once it was multiplied, once it was put it, and now it is divided with x into y and z. And so this will become more simplified. So I have only 1 upon x d square dx square into x, 1 upon y d square dy square into capital Y, 1 upon z d square dz square into z, plus 2me h cross square equals to 0. So this is how I am getting the different expressions, the different terms in the same expression. Yes, I have terms, but they are pure terms. There is one which is containing only x, only y and only z. This is how we are going through the separation of methods, how the one equation is dividing into 3 equations. This is the process which is going on. So now on rearranging, first I will separate the x part. One by one will separate. So I have this expression, and different terms are containing x as well as y as well as z. So first of all I will take the x part on the either side. So I will take 1 upon x. You can see on the slide it's very clearly given, that is 1 upon x del square del x square into x equals to, now I am taking the y as well as z as well as 2me on the either side, because now my focus is just on the x part. I am not intervening with the y and z, that what will happen to y and z, because now I am only my only concern right now is for the x part, because I am trying to develop that x part. So this is 1 upon x del square del x square, and the y expression, that is 1 upon y and that thing, and 1 upon z and 2me on the either side. Now the left hand side of the above equation, you can see that it is a function of x only, while my right hand side is a function of y as well as z only, and therefore the solution of left hand side and right hand side, because it is an equation, both the terms on both the sides are equal, so it must be equal to a constant. Because my left hand side contains x and my right hand side contains y as well as z, so I am putting it to a constant. I am putting both the equations to a constant which is containing nothing, neither x nor y or z. It is just independent of x and y and z. So I am keeping it as k1. So let 1 upon x del square del x square into x equals to k1. And now the right hand side is also equal to k1, that is minus 1 upon y del d square dy square y minus 1 by z d square, that is the other side, it is equal to 1. Now once this is obtained, the right hand side, now this equation, the right hand side 1, now this is my original equation, because from the main equation I have separated the x portion equal to k1, and now I am left with the equation which is now I am taking as the final one. Now in this expression which is put it equal to k1, now from this I'm taking the y portion out. So one by one I'll take all the variables out. So I'm taking out of this equation, I'm separating the y portion on the either side. So this will become 1 upon y d square dy square y equals to, so y portion is now separated, equals to minus 1 by z d square dz square z minus 2me upon h cross square minus k1. So this is how I have, first of all I have separated the y x part on the either side, put it equal to 1. Now the term which is left, out of that I have taken the y part on the either side. Now I will put this equal to k2, another, because again the left hand side depends upon y and my right hand side depends upon z. So I am taking a constant which neither contains x and y, and that is a constant, I have put it equal to k2. So this is how a new equation is generated which contains only y, that is 1 upon y del square del y square into y equals to k2. And now again I am left with, that is minus 1 upon z del square del z square minus 2me h cross square minus k1 equals to k2. So this is the equation which is left, and this is again my final equation from which I will derive the third portion, that is the z equation. Again I will separate the z portion out of this equation. So this will become 1 upon z del square del z square into z equals to minus 2me upon h cross square minus k1 and minus k2. So now again there are two portions. I'll put the z portion equal to a constant, that is my k3, and the leftover part is also my k3. So finally, if you see the derivation, I have got three equations, that is x equals to k1, the y portion equals to k2 and my z portion equals to k3, and the thing which is left in the end is minus 2me upon h cross square equals to minus k1 minus k2 equals to k3. So on rearranging, I will get k1 plus k2 plus k3 equals to minus 2me upon h cross square. Because the energy is always additive in nature, so my energy is Ex plus Ey plus Ez. I will put this expression, because I have to talk in terms of x and y and z, I have to separate these equations. So that is why I am putting the expression, that is instead of E, I am putting k1 plus k2 plus k3 minus 2me upon h cross square. Instead of E, I am putting Ex plus Ey plus Ez. So for convenience, suppose I substitute k1 equals to minus 2me h cross square upon kx, because k1 was dependent, it is a constant which we have selected for the x portion. So k2 is minus 2me h cross square into Ey, and my k3 is minus 2me upon h cross square equals to Ez. So now and then, because earlier we have taken three equations, if you have seen, I have got three equations, that is one which was containing the x portion, that is 1 upon x del square del x square equals to k1, and then I have derived 1 upon y del square y del z square equals to k2, and then I have derived 1 upon z del square del z equals to k3. So simply in these three equations, now I am putting, instead of k1, k2 and k3, I am putting the values and getting the differential equation. So this will become del square dx upon x square plus 2me h cross square Ex into x equals to 0. So in those equations, I have just put it the values of k1, k2 and k3, and I am landed up to the three differential equations, one for x, one for y and one for z. Now for the because its solution is not relevant over here, it is all mathematical portion. So simply I am just jumping onto the solution. The general solution for the differential equations, you can see in the various maths books it must be given. So my equation would be x n into, or it is, you can see it is simply a differential equation which was seen in the 1D box. So my answer would be x equals to nx sine 2ab ex upon h cross x minus x0. So because I am not discussing the solution over here, it is simply as that which we have discussed in the one dimensional box. So by this we have got three wave functions, that is x, y and z for the free particle. So by the total wave function, because wave function is always multiplicative in nature, so this will become, that is x into y into z. So instead of the wave function x, I have got nx sine 2m ex upon h cross square 1 x minus x0, which you can see on the slide the solutions are given. I have just multiplied them. I have taken nx, ny and nz on one of the sides, that is in the initial portion, and I put it nx, ny and nz equals to capital N. So the total energy would become, my total energy, because the wave function is always multiplicative in nature and my total energy is additive in nature, so I can also add them. So now the quantization of energy levels, that is difference between the particle in free state and under bound state. Now usually what happens is that if you calculate, because the same formula I have also discussed in 1D box, whenever an electron jumps from one level to second level, let it be n and let it jumps to n plus 1, so my energy difference is E n plus 1 minus E n. So what was my formula in 1D box was n square h square upon 8m square. Instead of n I am putting n plus 1 square h square upon 8m square minus just by taking n. So once we have taken the difference, my formula is 2n plus 1 into h square upon 8m square. If you see the formula for delta E, you can see that delta E is inversely proportional to A, that is length of the box. As the length of the box increases, that is the value of A increases, the difference in the energy levels decreases. That is, the levels become very close to each other, very less amount of energy is required. So if the length of the box is infinite, that is in the case of free particle, there is no restriction on the length of the box. The particle is free, there is infinite space to move around. So in that case, delta E would be very zero. It would be almost approximately equal to 0. That is, particle, there is no, the transition could not, that is the levels are very close to each other. That is the classical mechanics, because in the quantization there was restriction. Yes, the particle can move from this level to, that is the leveling occurs. The quantization occurs in case of quantum mechanics. In the classical mechanics, there was a continuous pattern. There was no separation between the levels. The particle can go anywhere. So this is what happens in the free particle. That is, in case of free particle, the length of the box is infinite and the levels because of that the delta E value decreases. The value of the discrete energy levels becomes smaller and smaller, and the difference between the energy levels decreases. Thus the energy levels, they become very close together, and if the length of the box, it becomes infinite, thus we can say that whenever the free particle occurs, the quantization disappears and there is smooth transition from quantum behavior to classical behavior, and thus it is a limiting case which we have, and this factor we have already discussed when I was doing the 1D box. So the only difference is that when the particle is in the bound state, there is quantization, and when the particle is in the free state, the quantization vanishes. Now I am discussing about one or two questions on the free particle, that what important aspect is signified for an atomic model for a particle in free space and under bound state. So this is the simple case that in the bound state quantization occurs, whereas in the free state the quantization vanishes. If a particle in 1D box move under the constant potential in a space that has no boundaries, what does it mean? It means that the free particle, will energy be quantized in such a case? No, because the quantization vanishes, because the value of the A becomes infinite. So by this topic, now we have finished for particle in a box, because particle in a box topic in itself contains 4 topics, that is particle in 1D box, 2D box, 3D box as well as free particles. So today we have finished with the particle in a box topic, and now in the next session we will discuss about the next chapter in fact of quantum mechanics, that is rigid rotator. Okay, thank you.
There's no thank you, ma'am. Thank you so very much for giving us this session on free particles. Friends, you're requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on quantum chemistry. In our previous session we discussed on free particles. As promised, here we are again and we are going to start with a new chapter, and this chapter is on rigid rotators. And for the discussion on rigid rotators, we have with us in our studios Dr. Amita Dua. Dr. Amita Dua is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So let's welcome our guest Dr. Dua once again, and let's try to have more and more knowledge on rigid rotators. Hello ma'am, welcome to the lecture.
So now I'll continue with the new chapter, that is rigid rotator. And again in this like in the particle in a box, first we discussed about how because in actually if we see in all the quantum mechanics, in all the chapters of the quantum mechanics, what you will see that we always try to derive the Schrodinger equation. The main thing is that always in all the quantum mechanics chapters, the chapters which we discuss in the books of quantum, we usually do how the Schrodinger equation is derived for that particular system, and once the Schrodinger equation is obtained, this thing is obtained from the Schrodinger equation, how will you derive the wave function as well as the energy. And once the wave function is obtained, from the wave function you can calculate the properties of all the system. And the application of quantum mechanics, that where you will apply this value of energy, is spectroscopy. So with every chapter which we discuss in quantum mechanics, it is, with every chapter there is an additional chapter, that is spectroscopy is also, you can also study the spectra part, because it is spectro is actually the application of quantum mechanics. So now today we will discuss about the rigid rotator. In the rigid rotator we will discuss about spectroscopy also, but in the later lectures and all that. Today my focus is on the rigid rotator. Now the rigid rotator is the simplest case. That is because in chemistry actually we have got the diatomic molecules. So I am considering it is actually the molecule which I am taking as a in which the bond is fixed, because we are starting with that is the bond is fixed. Actually it is not fixed, because there is always, you know, the bond is not rigid. Actually in actual practice the bond is never rigid. If the bond is rigid, obviously it will break down, because there are always the vibrations, rotations and electronic movement in the bonds. In actual practice it happens, which we will discuss. Yes, we will discuss when this chapter is over, then I will discuss about all these things, that is the elasticity and all those things. But in the initial stages I am discussing that my bond is rigid, that is it is fixed and it is just rotating perpendicular to its axis. Suppose the axis is like this, then the bond is rotating like this. The bond will never rotate around its own axis because of that moment of inertia thing, which we will discuss. Yes. So now the rigid rotator is the simplest case of the diatomic molecule. Suppose the bond is there, A and B, and it is rotating perpendicular to the, suppose this is my bond and this is my bond A and B, and this is the axis, the bond axis. So my bond is moving, it is perpendicular to the axis. It is the simplest case of the diatomic molecule with the rigid bond length, that is whose bond length does not change during the rotation, and it is an important system as because it will later on it will help you in studying the rotational spectra of the diatomic molecules. Now first I will discuss about the classical treatment, that what was the classical, that in the classical treatment I will discuss that what is actually a rigid rotator, the design of the rigid rotator, and then in the quantum mechanical treatment we will discuss about the Schrodinger equation and all those things. So suppose I consider a diatomic molecule which consists of two atoms whose mass is m1 as well as m2. You can see on the slide the diagram is given. It's a rigid rotator which is rotating along the center of the mass axis. So suppose this is a bond, it is rotating like this, not like this. This is a bond, it is not rotating like this, but it is rotating like this. This is the most important thing which you have to note, because later on we will definitely discuss that why it never rotates along its own axis. It will always rotate perpendicular to its axis. Now consider a diatomic molecule which consists of the two atoms whose mass is m1 and m2, and they are connected through a rigid bond. It is a fixed bond whose length is r, equal to the distance between the two atoms of the molecule, because obviously of course we have got atoms over here in the chemistry portion. We have got two atoms, chemical system we are taking, and assume that the center of the mass of the system is fixed at point O. So this is the diagram which you can see, and the distance of the m1 from point O is r1, and the distance of the m2 from the point O is r2, and the total distance, that is r1, and that the bond length is r. Let this rigid rotator be rotated around an axis perpendicular to its own axis, okay, which is passing through the point O, and the interatomic distance does not change, that is there is no variation in the bond length, that is bond length is fixed. These are the most important things, that is why I am repeating again and again that my bond length is r, because in all my derivations at that time I will simply take I am taking r as constant. So you should know, because in the rigid rotator I am taking the bond length to be a rigid bond. Now for the microscopic diatomic molecules, because in quantum mechanics obviously we always deals with the microscopic system. For macro we always go for the classical treatment. For the microscopic diatomic system we consider the reduced mass instead of the individual masses. So for the system I am not taking a mass m1 or m2, no, but my concentration, my focus is on the reduced mass. Every time I'll instead of m I'll take nu. What is nu? Nu is my reduced mass. Now my total mass of the system, now you should know what is reduced mass, because there are in the expressions of rigid rotator there are few things which you should know. That first of all, you should know what is moment of inertia and what is reduced mass. So, I will discuss first of all both the things and then I will go. Now, my total mass m is m1 plus m2. Also, my reduced mass is given by the expression 1 upon nu equals to 1 upon m1 plus 1 upon m2. I will take the LCM simply, m1 into m2 in the numerator, this is m1 plus m2. On taking the reciprocal, nu equals to m1 into m2 upon m1 plus m2. Instead of m1 plus m2, I am putting capital M. Now, the reduced mass is always less than the either of the two masses, that is m1 as well as m2, and the lighter mass of the two will always have a greater contribution to the reduced mass. So, now simply my m1 is less than m2. So, in the expression for nu, what is my expression for nu? That is m1 into m2 upon m1 plus m2. Because m1 is very less, so it cannot be neglected in the multiplication part, but whenever there is addition or subtraction, we can neglect m1 because it is very small. So, this is m1 into m2 upon m2. So, m1 is neglected, m2 gets cancelled. So, my reduced mass equals to m1. So, this is simply that what is my reduced mass. Now, I will come to the kinetic energy. Because why I am discussing only the kinetic energy, why not the potential energy? The most important thing is because my bond is fixed, there is no variation in the length. Because there is no variation in length, it means that the potential energy of the system is fixed. So, my total energy is only the kinetic energy. My potential energy has become equal to 0. So, a rigid rotator which is rotating around a fixed axis has a rotational frequency. Suppose now that's why now you come to know that why I have taken the kinetic energy only, why not potential energy, because in case of rigid rotator potential energy is 0. Now suppose there is a rigid rotator whose rotational frequency is nu. Everyone knows what is the symbol for frequency, that is nu. So this will become nu rotational. And I have taken rotational velocity as v, the small v, I have written rot under it. These are the few expressions which you should know for all the derivation part. Now the rotational velocity is, what is my velocity? That is distance travelled in a rotation, and that is a circumference, obviously it is rotating in a circle, and the rotational frequency. So v rotational equals to 2 pi r into nu rotational. I have taken r out, 2 pi, this will become v rotational equals to r, 2 pi nu rotational. Now my 2 pi nu rotational is what? That was a rotational frequency, that the nu rotational was my rotational frequency, and instead of now 2, when it is multiplied by 2 into pi, this will become angular velocity, that is omega. So v rotational will become r into omega. This is the one thing which everybody should know whenever we going to study this topic, the rigid rotator. Suppose we have got v1 and v2 as the two rotational velocities of the two atoms with which they are rotating around the axis. For the first one, the velocity is v1, for the second one it is v2, and thus the kinetic energy of the rotator is, because we are doing the classical treatment, what is the formula of kinetic energy? Kinetic energy is half of mv square. So there were two atoms, mass was m1 and the other one has mass m2. Velocity is v1 as well as v2. Now up till now I am discussing about, I am taking the classical expression and after that I will convert it into the angular velocity. Just see. So my kinetic energy expression is T equals to, for the system, that is which is containing the two atoms, that is half of m1 into v1 square plus half of m2 into v2 square. Now because we are shifting towards the rotating models, whenever the rotation part is done, the angular part should be taken into consideration. So instead of V1, my V1, that is which was a rotational velocity, I am converting into the angular velocity. So my V1 is R1 into omega and my V2 is R2 into omega. So I am shifting from V to omega. This is how I am shifting. Now, so putting 3, this is equation number 1, that is V rotational. Second, the expression of kinetic energy is my expression 2. And the expressions of V is my equation number 3. Now I am putting these equations, that is equation number 3 in equation number 2. So the expression for my kinetic energy would become half into m1. Instead of V1, I am taking R1 into omega, that is V1 square. So instead of V1 square, I am taking R1 into omega square. Half of m2, instead of V2, I am taking R2 into omega square. You can see on the slide, it's very clearly written on the slide how the things are being changing. I am taking omega square out. This will become half of m1 r1 square, half of m2 r2 square and omega square out of the brackets. Now half of m1 into r1 square and half of this is my moment of inertia. So instead of this expression in the brackets, I am just taking I, that is I is my moment of inertia. So T equals to half of I omega square. This is the expression for the kinetic energy for the rigid rotator. Now before going into detail of Schrodinger equation and all those things, first you should know that how will you get this formula for moment of inertia. It is a simple derivation. Usually you can see most of the students get this derivation in exams also. That's why I want you to discuss this a simple derivation over here. So for the moment of inertia, from the location of center of mass as shown in that figure, the initial figure, that is figure number 1 which I have shown, m1 into r1 equals to m2 into r2. Now my total distance r equals to r1 plus r2, that is the diameter. The first equation is A and my second equation r equals to r1 plus r2 is, let it B. Using A and B, first of all, suppose r equals to r1 plus r2. From this thing, what would be my r2? r2 equals to r minus r1. Now m1 r1 equals to m2 r2. Instead of r2, I will put r minus r1. So this will become m1 into r1 equals to m2 r minus r1 in the brackets. Now simply I will open the brackets and multiply this thing. So this is m1 into r1, m2 into r minus m2 into r1. Again m2 into I have multiplied m2 into r. I am taking the r1 term on one side and r2 on other side. So this will become m2 into r equal to m1 r1 plus m2 r1. This I have done so that I can take r1 common. So this will become m2 into r in the brackets m1 plus m2 into r1. So by this I get r1 equals to m2 upon m1 and m2 into r. So by this I get the expression for r1. Similarly, in the same method, that is I have mentioned point 2 in the derivation, you can derive the expression for r2. So my r2 will become like this, which I have marked D, that is m1 into m1 plus m2 into r. So this is how my moment of inertia, now the formula of moment of inertia is m1 into r1 square plus m2 into r2 square. Okay. So if I put the expression for r1 as well as r2 into this thing, this will become m1. Simply instead of r1 I have put it m2 into r, which you have just derived that is why I have derived the expression for r1 and r2. So this will become m2 into r square upon m1 m2. So I have just put it the values of r1 as well as r2 and taking the square of them, and on solving and rearranging them I get I equals to m1 into m2 upon m1 plus m2 into r square, and what is my this thing m, the brackets one, that is nu, which was reduced mass. So another formula for moment of inertia is I equals to nu r square. Now for the rotating models, all the linear properties like momentum or velocity, they gets converted into the angular properties, because now we are more concerned, we are more focused for the rotating part, that is the angular part is more concerned. So I have made a small chart for you, that is the linear properties like linear momentum, which I have marked as P. Now in the angular properties, whenever we discuss about the rotational motion, instead of linear momentum we use angular momentum, that is capital L. Instead of linear velocity we use angular velocity, that is omega. This is what I have done. Instead of mass we take moment of inertia. So thus the classical kinetic energy for the linear system can be, for the rotating models it will become, now my kinetic energy was, earlier I have discussed, it was half I omega square. Now I multiply and divide by I and I. So this will become I square omega square upon 2I. So this is I omega square. Now what is I into omega? I into omega, because this will become L, that is the angular momentum. So my expression is L square upon 2I, which I will use in the quantum mechanics. So this is the angular momentum. Now these are actually some of the expressions which we should know in the classical mechanics. In fact, you have also studied in class 11th and 12th about the kinetic energy of the rotator and all those things. But now we will discuss about the main important thing which I want to discuss in the quantum mechanics. What you do in the classical, you must have done so many these things. In 11th and 12th also you must have read about the rotator, about all these expressions, the kinetic energy and potential energy. But now my main focus in the quantum is the Schrodinger equation, which is the actual thing which we have to discuss. And in fact, in the classical mechanics, we always say that yes, the rotator can rotate freely at any extent, which is actually not so. There are restrictions on the rigid rotator, which quantum explains that yes, you cannot rotate a rotating model to any extent, because it will lead to the rupture of the bond. The bond will break. Yes, there is rotation of the bond, but there is some limit to the rotation, which is explained with the help of quantum mechanics. So the thing is, why we are discussing about the quantum mechanics of the rigid rotator? Why there is a necessity of discussing about all those things? Because according to the classical mechanics, when we study the rotator in classical mechanics, we see that yes, there could be any value of L, or there could be any value of velocity and whatever, and the rotator can rotate to any extent. But actually this is not so. The quantum explains, yes, it rotates, but to a particular extent. There is a restriction on the rotation, which is explained by the Schrodinger equation, because in the Schrodinger equation finally you will see after 1 or 2 lectures you will get to know that I will introduce a quantum number, that is m is introduced. This is how the quantum number m was introduced in the quantum mechanics. From this chapter only m comes into the picture, that yes, the rigid rotator moves, but there is restriction on the rotation part. So now today we will discuss about the Schrodinger equation. How will you always in the Schrodinger equation, my basic equation is always H psi and E psi, and my H operator is the Hamiltonian operator, which you always knows. And the one important and because my Hamiltonian is kinetic energy plus the potential energy, because we are taking the rigid rotator. Rigid means the length of the bond. For chemistry point of view, we have got a rigid bond. That is, although the bond is, yes, there is rotation, but the bond is rigid, the bond is fixed, so there is no change in potential energy. So whatever changes or the energy develops is all the kinetic energy. So I am not considering the potential energy over here, I have only the kinetic energy part with me. And one more important thing is, because it is a rotator, that is why I'll discuss about the that is the rotating part, not the linear part. That is the angular part is taken more into the consideration. That is one thing more, that we will talk more in terms of the polar coordinates, because the atom is not moving like this. We are not discussing about the Cartesian coordinates, that in one axis, in x axis or y axis, but it is like a rotating model. The angles are made. So I have to change my coordinates. Instead of the Cartesian coordinates, in the particle in a box, we are always concerned with the Cartesian coordinates we use, that is x in x terms or y. You must have seen in the first session only I have discussed about the separation of variables, that is x, y and z. The wave function was in terms of x as well as y and z. But now it is a rotating model. I am not concerned about the Cartesian, yes the Cartesian, but my main focus is on the angular part. I will convert the Cartesian coordinates into the polar coordinates, where the angle comes into the picture, like theta part or phi part, that kind of thing. Otherwise in the wave function we take x, y, z, but now in case of wave function we will take theta, phi and all those things. So this is the basic difference in in solving the particle in a box and in case of rigid rotator. So the most important thing is that in those cases, in particle in a box or free particle of those things, we take the Cartesian coordinates, but in the rigid rotator like these things, where there is movement in like a rotator, the angular part is important. So the rigid rotator can be solved for energy. It is of course for any system in quantum mechanics, whenever the Schrodinger equation is solved, it is solved for the wave function as well as the energy. So whenever it is solved, it can be derived. First of all, I will derive and then we will solve. So whenever this is derived in two ways, one in which the angular momentum, because ultimately which operator we have? The kinetic energy operator. We have with me the kinetic energy, because potential energy is 0, where the angular momentum of the kinetic energy operator is reduced in polar coordinates, and second, where the Laplacian term of the kinetic is. So just keep in mind, there are two ways by which I will derive the expression of the Schrodinger equation in the rigid rotator. One in which the angular momentum part of the kinetic energy operator is reduced to the polar coordinates, and second in which the Laplacian operator, which is seen in the kinetic energy operator, is reduced to the polar coordinates, because ultimately I need the things in terms of theta and phi, that is angular part. So deriving the Schrodinger equation, so my total energy is the sum of the kinetic energy as well as the potential energy. In this system, we assume the potential energy equals to 0, because the distance between the two atoms is fixed during the rotation, and thus the total energy is solved by taking the kinetic energy only. From the kinetic energy expression, what I have just derived the expression for kinetic energy, that is L square upon 2I, which is in the numerator. Since the moment of inertia in the denominator is specific to the system, and thus it has got the, what is moment of inertia? Actually what is moment of inertia? Moment of inertia is mass and nothing else. Because the mass of the system, there are only two atoms, M1 as well as M2, and we are not taking M1 and M2 at any cost. We will take the reduced mass only. I will not take, in any case I will not take M1 and M2. I always try to take the reduced mass, that is mu. So if you try to get the Schrodinger equation, the kinetic energy is L square upon 2I. So there are actually two methods. I have already told you that by two ways I will discuss the Schrodinger equation. My first is I will derive the Schrodinger equation where the angular part is taken into the consideration, and my second part is where I will take the Laplacian operator. So once the Schrodinger equation is obtained, we will then get the wave function as well as the energy of the rigid rotator. So today this I'll discuss in the last chapter, because these are the two whole derivations which I have to do with you. So these are the two derivations I'll discuss in the next, and I'll continue with the rigid rotator in the next lecture. Thank you.
Thank you, ma'am. Thank you so very much for giving us this session on rigid rotators. Friends, we are going to meet again very soon and would be discussing more. Till then, take care, goodbye. And yes, if you have any query, do write to us at info.cec@nic.in. With this note, thank you, ma'am. Thank you once again.